Welcome back to the second episode of the Basics of Protection Relay Testing powered by Minnatrel Power Systems. In this event, we will be looking at a couple of interesting features that is present in your Omicron test universe. We will be looking at a state sequencer module and figuring out how to generate a sequence of events. We'll also be looking at how do we ramp up our parameters such as our current and voltages, and what would be the reaction from the relay. But before we start, here is a small recap of what happened in the previous episode. Today, we have quite a few interesting concepts that we will be looking at, and we'll start. So when you talk about faults are not necessarily instantaneous events, right? So faults happen over time. We call them incipient faults, but faults also follow a certain set of sequence, right? So that is what we'll be focusing on today. So we know that a system can be switched off completely or de-energized and a fault could happen, or we also know that when a system is running normally, a fault could still disrupt your entire power system, right? So to look at it, we need to ensure what is exactly happening in case of a fault, right? So what I have shown over here is nothing but a very simple system that I have created over here. So you can see that the system has a source and a particular load, right? So here we have a 110 kV system that is connected to a load of around 50 megawatt and 2 MVAR, which is connected via a transmission line of length of 10 kilometer. Now, multiple events could happen within your system. For example, a breaker can open and close, and on top of it, disturbances such as load variation, source variation, as well as any fault also could happen in your system. So what we can see from the waveform that is below over here is, so the first waveform that you see over here is nothing but the voltage waveform, and the second waveform that you see here is the current waveforms as measured by the relay that is connected on the source side, right? So here we have a relay. You can see that there is a relay that is being mentioned over here, and on the event list, what we have essentially done is, I'm assuming that an event has happened, that is in this case a 3-phase fault has happened in my system at a time of 300 millisecond. So how does your waveform actually behave like that? So what we are assuming is that the breaker, that is circuit breaker A, is closed, and after 300 millisecond of simulation, a fault is assumed to occur at the line. So initially there is going to be a particular voltage and there is going to be a particular current that is flowing or that is being measured by your relay. But the moment a fault happens, you can see that the current and the voltages have been disrupted. So in this case, what you essentially are seeing is that the voltage has dipped down to a very low value and the current has increased to a very high value. So state 1, what we call here, is called the pre-fault state. So essentially the normal operating conditions of your system is what we call as a pre-fault state. And you can have a faulted state. So in this system, in this time, the fault still is existing in your system without being cleared. Now, if the fault has been cleared, then you will have what we call as post-fault state. So we have a pre-fault scenario, then we have a faulted scenario, and then we have a post-fault scenario. Now this is going to be the sequence of events that are being seen by your relay as well. So as protection testing engineers, it is up to us to test a protection function as close as to the actual function as possible. So here again today we will be looking at a very simple overcurrent protection and how we could test it using the state sequencer and ramping modules. But before that, let's jump quickly into test universe. So here you can see my test universe screen, and here you could see my quick CMC, which is essentially a virtual front panel, and you can also see what is the ramping module. So we can have ramping up, and you have the pulse ramping, and you have a state sequencer, right? So let's just go into quick CMC. So quick CMC, or with respect to any software module of test universe, we know that we have to follow the Ohm law. So what does the Ohm law say? The Ohm law talks about O for object configuration, H for hardware configuration, and M for module configuration. So the first thing that I need to do here is configure the test object, right? So here we go to the device settings, and I can name my relay. I can call the manufacturer, and if I have any model number, I can just fill it up over here. But more importantly, I would like to fill up the CT ratio as well. So I have a CT ratio of 1600/1. I'm just filling it up and clicking OK, and done. So once the test object configuration is done, I have to go to hardware configuration. So once we are performing the hardware configuration, it's very essential for us to configure only what we are going to be using. For example, in overcurrent protection, we are not going to be using the voltage. So I'm going to be clicking this to be not used. And we are only going to be using the one channel of current, that is current channel A or current output A, as you can see on the screen. I'm just going to click OK. And I can change the name of the test output signals. For example, if we want it, we can keep it as any particular name that we want, or I could have the default value that is same as my test module output signal. Now here we have configured the trip as well as the pickup signal, which we have connected to the relay accordingly. And I'm going to click apply, OK, and we are done. So the moment you have configured the hardware, you can see that only the analog signals that you have selected is appearing over here, right? So the next thing that I want to do is I want to perform a measurements check. The first thing that we do whenever we do relay testing is we perform a measurement or a wiring check to ensure that the phases are connected correctly and there is no open circuit or overload condition existing anywhere in the system. Okay. So for that, I am just going to inject a value of 1 amps, and if I want, I can measure it or view it from the CMC itself. So what I'm going to do is I'm just going to show you guys the camera as well. Yes. So yeah, so you can see the camera, I hope. And what we have done is we have just pictured the relay over there. I'm just gonna change it to show you the measurement screen. So in this case, our current channels are connected to the generator terminal series, that is Gen TRM. So what is the next step? I have to select a particular input, that is here I have selected as IR, and I'm just going to click start. So the moment we have started the injection, you could see what is happening in the corner. You can see that the current is being injected, and you can read the same current in the relay as well. Now, if you want to see it in the primary, you can just go change the settings in the relay itself. Done. So now I'll be doing the same thing for the other two phases as well. So without stopping the injection, we could just right click and make it 0 and make any one nominal. So now I have done for the Y phase, and next is for the B phase. Okay. So if I want to see this in PCM itself, I can just go to PCM 600. You can see that we have already communicated with the relay. So you can see the green tick that is existing over here, and right click, go to signal monitoring. Now in signal monitoring, I have set up a place for measuring the 3 phases, only the terminal currents. So here you just need to switch on continuous reading. So if it's green, you can see the continuous values. I'm going to go back to quick CMC and right click on equal magnitudes, which means that all the 3 phases will now be showing 1 amps, and the equivalent in PCM 600 will be 1603, 1602 with certain level of errors. So once we have performed the measurements check, we know everything is working properly. What is the next step? Now there are ways in which I want to assume a pre-fault condition. So when we talk about pre-fault condition, the most commonly used pre-fault conditions are going to be your no load condition, in which you're not going to be having any load, maybe only voltages are present, or you can have 50% of the load connected or 100% of the load connected. To assign it, what I'm going to do here is, you can just see here there is something called pre-fault, and here you can select a particular percentage of the load. So if we talk about 50% of the load, and if I hover my mouse over here, you can see that the moment we have clicked on pre-fault, it is injecting. You can see that the current is being injected, and you can see the measurements in the relay and the measurements in PCM itself, that 500 milliamps is being injected, and you can see the equivalent value as 800 amps over here on the primary side. So what is the actual meaning of this? Essentially, the timer has not started and we have not actually injected any fault, but the quick CMC gives you an easy way of injecting a pre-fault set of events. Now, if you have your voltages connected, please understand that pre-fault always injects 100% of the voltage. And when we talk about load, only the current is going to be varied. So 100% of the current is going to be 1 amps, and 50% of the current is going to be 0.5 amps, 10% is going to be 10% of your nominal value. So this is very simply what is pre-fault. So once pre-fault is running, I can enter any value over here. I can enter any fault value, and when I'm ready to inject it, so we know that pre-fault has been running, and for a set amount of time, we do not actually calculate time when we talk about pre-fault. And when I press start, then the fault has been injected, the relay has picked up, and the timer has given me a time of 4.700 seconds. You can actually see that the relay has also tripped. You can see the red LEDs that has come up over here. And this is essentially pre-fault. So I'm going to show it again. I'm going to press pre-fault. So you can see what is being injected over here. 500 milliamps is being injected. The same thing you could see in the relay as well as in PCM 600. Now I am going to start my injection of fault. So I've selected a set value. I can make changes even while pre-fault is running. So I can make it, let's say 5 amps, all the 3 phases. So right click and make it equal magnitudes and press start. And you can see in PCM that I have close to 8000 amps flowing. The relay has tripped, my kit has stopped injecting, and the current value has become 0. So this is a very simple way of showing what is a sequence. So what was the sequence that we followed? So the first thing was we injected pre-fault till we were ready to inject the fault. We injected the fault and the relay has operated, and we have measured the trip as well as start time. Now, if I want to make changes while I'm injecting, right? So let's say that I'm making everything equal to 1 amps and will press start. So once you have pressed start, you can see in PCM, you can see in the relay that we are injecting full load, that is 1600 amps. Now, if I want to make any changes, I can just select it and make changes, and the current is automatically being changed. So because we injected 2, the relay right now has picked up. Now the moment I make it nominal, you can see that the relay has dropped over here. Now if I want to make changes for multiple parameters at the same time, so for example, if I want to change R phase current to 0.5 and Y phase current to 5, and while the injection is going on, right? So what I can do is I can just click on hold values. So now it is being held. You can see over here in phasor view that 1 amps is being injected. Coming back to our set mode, I can just change it to 0.5 over here, and I can make changes to Y phase, 5 amps, and if I want, I can make changes to the angle as well, right? And here you can see that still 1 amps is being injected. You can see the measurements in the relay as well, that all the 3 phases 1 amps is being injected. Now once I'm happy with the changes that I've done, I just click it back, and you can see the relay has picked up. You can see how much is being injected right now, and the relay has actually tripped. So here what we have done is we have selected a particular pre-fault. So if I'm assuming that 0.75 or 750 milliamps on all 3 phases is going to be my pre-fault. So I can just click start. Now I'm assuming that this is going to be my pre-fault values, and I'm holding them so that I can make multiple changes. I'm going to make this 3 and I'm going to make it equal. And the moment I click hold values again, the relay has picked up and the relay is going to trip after a certain amount of time. So this is another way of deciding what could be the sequence of events. Now, in case you want to have more than one certain sequence of events, that is when you will be talking about the state sequencer module. So to go to the state sequencer module, first we have to close QuickCMC. Now there is something that I would want to add over here, is a quick note. So let's say that you're doing hardware configuration. Now you want to maintain this hardware configuration for multiple purposes, right? So what I can do is I can just select hardware configuration in general tab, click on export, and I'm just gonna save this as a hardware configuration file and click it as save. Now I'm gonna close QuickCMC. It's gonna ask if I want to save. No. Go back to my test universe page, click on state sequencer. So state sequencer is a very powerful tool because you could design and designate any given set of states, and you can play around with multiple set of waveforms. You can play with your binary inputs, binary outputs. You can have a very complicated triggers as well to change from state to state. So this is the main view of your state sequencer. So again, we'll be following the same test object, O for test object configuration, H for hardware configuration, and M for module configuration. Now in hardware configuration, I do not want to do it again. We do not need to do it every single time. We can just import a hardware configuration. I have saved it in my desktop, OHC. And the moment I have done this, you can see that everything has changed as per my particular requirement. So essentially what I'm doing is we do not want any voltage outputs. So we have just selected the current outputs. Now here I can also select different types of binary outputs. So if I want to simulate a circuit breaker command or circuit breaker status from my kit into the relay. So if I want to give an input to the relay from my quick CMC, we can use the binary output as well. But for the time being, I'm more focused on the triggers, right? So here I'm going to be having 3 states. So let's call state 1 as pre-fault, wherein we are assuming that 50% of the current is flowing. And next, we are going to insert a state, calling this a faulted state. And here, let's take 5 amps as our value. And once this is done, I want to have another state for post-fault as well. Post-fault, let's assume that it's coming back to a lower value of current. Okay. So here you can see what is going to be the waveform that I have created. So till 1 second, we are injecting pre-fault value. And we'll be injecting a fault of 5 amps. Now the shifting from state 1, that is pre-fault to fault, is a time-based trigger. We can go to the trigger tab, and we can see here what is the condition for state termination, meaning at what point does this state stop and goes to the next one or complete your injection. So you can see here that there is something called timeout. So I've selected timeout and we have kept the time as 1 second. So let's say that we want to inject the pre-fault for 1 second. It's as simple as this. And there is no binary trigger logic, which means we do not need any trip or pickup for this state. But for fault state, what I want is, the trip time was somewhere around 4.7. If you want the actual calculated value, we have our Excel sheet, and this is the formula. So we could just calculate it. So for 5 amps, the calculated trip time is around 4.67 seconds. And we need to ensure that the state does not time out before that. So either you can disable timeout, which means only binary trigger is used as a condition. And what is the condition? My trip command or my trip input should become 1. I'm not going to use my pickup. I'm going to use my trip as my input. We can also use logic. For example, if we want to say that start and trip both should have been high, only then the binary trigger condition will be satisfied. I can have AND conditions, I can have OR conditions, in which we could decide what is going to be the trigger condition with respect to your binary outputs. The binary inputs. So the reason why I prefer to use timeout is for safety reasons, right? So we have connected as per our schematics, and we know that the relay and the wiring is done correctly. But in case the relay fails to operate, we should not be injecting the fault for a very high amount of time. So that is the reason why I would prefer to use timeout. So timeout here, we know that the relay is supposed to trip within 4.75 seconds. So I can keep somewhere, we can keep somewhere to up to 8 seconds, right? So we are allowing up to 8 seconds. If the relay trips within 8 seconds, that is going to be your binary trigger, or the state is active for at least 8 seconds, then it is going to go to the post fault state and it will be present for 1 second. Now here for fault condition, we have given an AND gate of both trip and start, which means that the termination is, or the trigger is only achieved when both the inputs, both the trip as well as pickup input becomes high. We have certain more settings. When do we start the test, and is there any binary outputs? Do we want to make it high for a particular event? We are not going to be changing any of this. So once all of this is done, we can see what is going to be our waveform. We can see that at 1 second, my fault state becomes high and it is going to exist up to 8 seconds. But if a trigger is generated before that, then it is not going to worry about it. It is going to go to state number 3. That is going to be the pre-fault, or sorry, the post-fault state. So you can see post-fault over here, and you can see fault, and you can see pre-fault. So you can see what is going to be the waveform that we have generated. Now, I not only want to do the testing as a sequence of events, we can also check whether the time assessment that we are getting is correct. So here I want to measure the fault time, or sorry, the trip time, right? So to ensure that I have a trip time, I can assign timers based on a particular state. For example, we are going to measure the trip time over here. I'm going to ignore before fault, which means that the timer is not going to be looking at anywhere till the fault state has come alive. Start when the fault state has started. When should the time stop? The time or the timer should stop when trip becomes 0 to 1. So when the trip output of the relay becomes high, then the timer should stop. We can also enter a nominal value. So going back to the Excel sheet, we can see that the nominal value was 4.67. Coming back, I'm going to enter it as 4.67. If you want, we could enter an allowable deviation. I'm going to have a deviation of plus or minus 100 millisecond as a deviation that is allowable. And once the test is completed, we can see what is the actual time and what is the actual deviation. If the time that we get, or the trip time of the relay, is between 4.57, that is minus 100 milliseconds, and 4.77, that is plus 100 millisecond, then the assessment will become pass, right? So what we have done over here is we have created a sequence of events. So we have a pre-fault, a fault, and a post-fault state. We have assigned currents based on a certain set of conditions, and we have also assigned a time assessment. Now the only thing that we have to do is just press the start and execute the test. You can see that the test is being executed, and we can see that the relay has tripped, and that actual time is around 4.704. So this is the actual time. This was the calculated time. We have a time deviation of around 33.80 millisecond, and thus we can say that the test was successful. So I'm just going to reset the LEDs in the relay. And for doing the test again, if you want to perform the test again, you have to press the clear button. So all the test results are cleared. So please be very careful about it. And I can change the timeout over here So for easy viewing, you can see what is happening within the relay as well. So the test has started. For 5 seconds, we'll be injecting 500 milliamps that you can see over here. And now 5 amps is being injected till the trigger condition of both pickup and start is being satisfied. And over here, we could see what is the actual time and deviation as well. Now this becomes very powerful when you want to do multiple tests. So generally we test close to 5 test points. With for a particular curve, we will be testing up to 5 test points. And we could create individual states for each type of fault. All I need to do is just clear this. So if I want to make it, let's say 2 amps, and I'm going to have 2 amps over here, then what we could do is you can just copy, paste, and we could name it fault number 2, and let's have this fault to be 5 amps, and I want to have a reset. So every time a fault has happened, we are supposed to allow the relay to reset. So let's have a post fault again, and let's have another fault. So what are we having here? We have 3 faults, each with different parameters. 3 different faults, one fault of, I'm going to change it to 2 from 4 amps, and then a post fault, and another fault of 5 amps, and then a post fault, and another fault of 6 amps. So we can have 3 faults, and I can have 3 different time assessments as well, right? So ignore before fault 1. So for 4 amps, the calculated value is 5.51. Let's enter it in the nominal value 5.51. I'm going to add another one. Let's call this trip time 2. Ignore before fault number 2. Start when the fault number 2 has started, and stop when trip has become 0 to 1. And fault number 2 is 5 amps. So we had 4.67 seconds. And I'm going to give the allowable deviation to be 100 millisecond. Let's add one more. I'm going to be calling this trip time 3 for fault number 3. So ignore before fault number 3. Timer starts when the state fault number 3 starts, and the timer stops when trips become 0 to 1. Calculated value for 6 amps is going to be 4.15 seconds. Let's enter this 4.15, and deviation plus or minus 100 millisecond. So we have created 3 different faults, each having its own post fault value of 2 seconds. And all we have to do right now is just press the start. So I can just see in PCM 0.5 is being injected for 5 seconds, and 4 amps is being injected. Now how 5 amps is being injected, post fault, and fault number 3, 6 amps is being injected. So here we could see what is the actual time as well. So the deviation, actual time, and nominal time. So nominal time is going to be your calculated time. Actual time is your actual trip time of your relay, and the deviation. So essentially what we have done, we have made this Excel sheet redundant, right? So in this Excel sheet, we have done the same thing, and everything is calculated using the formula. But in case of state sequencer and time assessment, we can give the time assessments over here. And the beautiful thing is, once you're done with this, I can go to the report view, and we could see what is happening, what are the test settings, what are the test time assessments that is available, and the waveform that we have injected as well. Now this is one of the best ways of showing a sequence of events, creating a sequence of events based on your prior knowledge, as well as if you want to automate a certain set of faults like what we have done over here. We have just automated 3 faults, each with its own pre-fault and post-fault, and we have just checked what has actually happened within my relay. Now, this is a very powerful tool in the sense that we could play around with not only current, we could have voltages. If I want, we could even set it with respect to impedances. So we can inject a particular impedance shot. We can inject in terms of power. We can inject as faults directly, or we can inject it in terms of symmetrical components. So we can even simulate breaker opening, breaker close by using the binary outputs. So we can configure, we can have a state in which we can just assume that the binary number 1 or binary output number 2 is being assigned to give a command to your relay. Now, you can even use state sequencer to test accidental energization in case of generator protection. You can test auto reclosures, or you can automate a multiple set of faults. It can be something as simple as if you want to do measurements check and you want to do a per phase method of doing it and you're doing it repeatedly, we could have a state sequencer in which each state represents one phase current, and you can have R, Y, B, and 3 phase. So it all depends on your creativity and your imagination. The next thing that I want to show today is the fact that when we talk about parameters that is varying based on a type of fault, we notice that it is not abrupt, right? So whenever there is an increase because of a fault, that is going to be a sudden change. So that could be easily simulated using state sequencer, just like we saw now. So if I want to prove that from a normal working condition that we can see over here, the change because of the fault, the change in current because of the fault was very abrupt. So that could be easily been simulated or done using your state sequencer. But if I want to do it, and if I want to vary my parameters in a more smoother and slower value or slower way, either to determine what should be the pickup or to determine what should be the drop off of a particular protection function, then we use the ramp function. Now, coming back to QuickCMC, we know that we can increase and decrease a particular parameter in a smoother way using the step or ramp function that is available in your QuickCMC. So I'm just going to go import the same hardware configuration because I do not want to be playing around with my voltages. So let's import. Let's see. Done. Apply. Okay. And here we are good to go. So right now, what we can do is, let's say that we want to determine what is going to be the pickup of a particular phase. So we have already calculated that the expected pickup was around 1.142 amps. So what we can do is just go to QuickCMC 1.13. Let's start at 1.13. The trigger is pickup, not trip. So I want the trigger to be pickup. So we have selected pickup over here, and let's ramp the signal, that is IR, by in terms of magnitude, and we can give a step size of 0.01, that is 10 millisecond. Now I can start injecting, and if I press the up arrow, you can see that it has become 1.140 because we are increasing it by step size of 10, and the relay has actually picked up. But if I want to do this in a more easier and automatic way, all I need to do is just select auto step, let's decrease the step size 0.001 1 milliamps every 1 second, right? So now let's press start and press the up arrow. So you can see that 1 milliamps is being incremented every 1 second, and we just need to wait till the relay has picked up. The relay has picked up, and it has picked up at around 1.140. Now this is a very simple way of ramping or changing smoothly your parameters based on a particular step size and a particular step time. Now we can not only ramp magnitude, we can ramp the phase, and once you have selected all the outputs, we can ramp it up with respect to the frequency as well. So if I want to ramp up the frequency, then we can ramp the frequency as well. But Quick CMC is meant more to be on a quick and a dirty way of doing the testing actually. So let's look into the more advanced ramping module. So ramping module is just a magnified and easy to use way of what we have seen in Quick CMC, but it makes things more visual for you. And we can have multiple triggers. We can have multiple logic between triggers like what we saw in state sequencer as well. So let's O for object configuration. Let's not be worried about that. H for hardware configuration. I'm going to be importing a hardware configuration that I've already saved. Apply. Okay. And now I want to do two things. I want to check at what time or at what current value does my protection relay pick up, and I also want to see at what point does my protection relay drop off, right? So generally for any numerical relay, the pickup and drop off value should be close to each other, but in some cases the acceptable drop off by pickup ratio is around 95%. So the drop off value can be close up to 95% of your pickup value. So just like how we ramped up in Quick CMC, I'm going to be selecting a particular signal. Here again, we can select a set mode. We can set it as symmetrical components, as powers, or even impedances if you want to ramp up impedances, but that is for another time and day. So here we have selected IR, and you can notice that there is something called IR and there is something called IR plus, right? So here I'm just going to select IR. Let's start it at 1.12, and we can increase it to any high value. Delta will be the change in your signal. So the magnitude that I want to change, the quantity is magnitude that I want to change. I can change it here 001, and time period between two steps, that is time step. Here in case of ramping module, you can have a finer control. So the key thing that we saw was I can control the frequency of a particular signal alone. In Quick CMC, we can only control frequency when you have all the outputs selected. And I can have a very small step size, right? So 1 milliamp every 100 microsecond. If you want, we can change the d by dt directly, right? So if I want to change the d by dt directly, we can change it here as well. So we can see that it has around 301 steps, but the total test time is around 330 millisecond, right? Okay. So now we have ramped up. Let's ramp it down. I'm going to be selecting the same value, and let's see at what point does my relay actually drop off. So it's gonna be 100 microamps, 100 microsecond, and everything is going to be in minus because we are ramping up and ramping down. So you can see what is the waveform we have over here. We have ramp 1 that is ramping up, and we have ramp 2 that is ramping down. Again, we can set any binary outputs that we want. Trigger plays a very important role. So we can have a key trigger. For example, if you want to start a ramp or stop a ramp, because with a key or keyboard key, you can select key pressed and you can define any instruction. You can have a pop-up box which says press a key to start or stop. And if there is any delay that you would want, you can specify a delay. And here we are specifying the trigger logic. Now, we are not worried about trip over here. The only thing we are worried about is pickup, because we are going to be playing with the pickup and drop off. Okay. So once I have selected what is going to be the ramp state, now coming back to ramp assessments. Now, by default, there is a pickup and drop off assessment that is available for you. Let's not disturb it. The signal is going to be IR, but we know what is going to be the nominal value, right? So the nominal value, we have calculated it to be around 1.142. So let's just give it as 1.142. And the drop off, I'm again assuming it to be equal to my pickup. And we can have a slightly higher deviation. Yeah, I'm going to have a 50 milliamps deviation, and the actual value and the deviation will be shown over here. Now, if I want to perform the test for quite a bit more time, then we can just change the DT. So every 100 microamps, every 100 millisecond. So this is going to take an estimated time of around a minute. So let's reduce it a bit more further. 0.1, right? Okay. So all we have to do is now press start, and let's reset the relay. You can see in PCM that only the current is being increased in one of the phases. It's being ramped up, and here in ramping, you could see what is the graph that is being shown over here. And you can also see here in the bottom, you can see what is the value of current that is being injected at this particular point. Okay, so now we have got the pickup, and from pickup, your ramp number 2 has started. So from pickup, my ramp number 2 is going down, and essentially you can see that we have got a pickup of around 1.140. Our nominal was around 1.142, but here we could see that our drop off did not happen. My relay did not drop off till the ramp has completed, till that is 1.120. Now, if you are calculating it to be 95% of pickup, we have to allow it up to 1.08, right? So I'm going to change it. Let's go to drop off. Let's change the ramp to 1.08, and let's change it to 1.08. Now this is going to be the pickup and drop off. Now I not only want to measure the pickup and drop off, let's try to, we need to assess the ratio as well, right? So why should we do that in calculator as well? So there is something called calculated assessments, wherein we can select a particular X and Y, and we can have simple formulae, right? So X divided by Y, or in terms of percentage, if I want X divided by Y into 100%, average X minus Y by 2, things like this. So let's see it in percentage, right? So nominal, we know it is 95%, and ramp assessment, we have selected, we have made it to 1.080. Click start. You can see that my analog inputs, that is IR, is being ramped up slowly from 1.120. That is the start value that we have selected. Now it will ramp till 1.150 if the trigger does not come. If the trigger has reached, if you have triggered it, so you can see that the trigger has come somewhere around 1.140. Then from that moment onwards, it is going to ramp down, or the ramp number 2 is going to be enabled, and ramp number 2 is going to start from ramp 1 and it is going to drop down till 1.08. That was the approximate calculated value of the drop off that we have actually done. And now the test has completed. You can see ramp 2 has started here and it has stopped somewhere over here. Going to the ramp assessments, you can see what is the nominal value is 1.142 for pickup, and drop off it was 1.080, and the actual was around 1.140 and 1.117. So the assessment is right. So we have got something close to it. Now to do a calculated assessment, I have just kept the percentage. So drop off divided by pickup into 100%. Nominal was 95%, and we have got 98.01%. Now, if I want to change, or if I want to do the test for another signal, we could just select another particular signal. So we have selected IB over here, and you can see that automatically it has changed IB. If I want to maintain some current in IR and IY while ramping only my IB, I can set those values as well. So whatever is blue, we can set those values, and whatever is gray would be taken from the ramp. So in this case, what we have done is we have selected 1 amps and 1 amps in IR and IY, and only in the B phase we are injecting the ramping, or we are ramping the current only in B phase from 1.120 to 1.150. And I can have different ramp states. So for ramp state 1, I'm going to keep this, we'll keep this as, nominal value. And for ramp state 2, we need to select ramp state 2, and we have kept it to be nominal value again. Now, if we press start, you can see in the relay measurement that IR and IY will be seeing full current, that is 1600 amps, and IB, that is the B phase, will be slowly ramping up till the pickup has come. So you can see over here that we have ramped. Now it has, the relay has picked up, and we can see what is happening with the ramp while it is going down. That is your drop off. We can also see what is happening with our binary input signal. That is, you can see that the pickup signal is still existing. So that is what we want. And now it has stopped. So here we have seen that it's 1.139 and 1.116 as pickup and drop. Now in some cases, especially when you're doing in a manufacturer side, you may want to have a statistical value of this. For example, what is going to be the average pickup and average drop off? So right now we have done 2 tests, one for R phase and one for B phase. Now, can I have an average value, or can I have multiple tests that could be done and calculate the average value? So here you can specify, go to the general tab, and you'll be able to specify the number of repetitions. I'm just going to have 1. So let's repeat the test one more time, and I want to calculate the average value as well. So in this case, let's select Y phase and ramp number 2. I'm making everything 0. So only only Y phase is going to be injected, and B phase and R phase is going to be 0. But we have to do this 2 times. So here you can see ramp 1, that is 1 of 2, that is the first test is going on. We can see what is the current value that is being injected in Y phase. We can see the same in the relay as well. And here it is ramp number 2, that is the drop off that is being performed. If we go to PCM, we can see the same thing that is being shown over here as well. You can see that the current is being slowly increased. So there are multiple ways of testing a particular protection function, and this is a more cleaner way of doing it. So here is the second ramp, that is ramp 1, test number 2, that is repetition number 2. If you want, we can have multiple signals that we want to ramp, and you can ramp a magnitude and you can ramp the frequency. We can have multiple ramps, n number of ramps that we could have. But at the same time, if I want to visualize what is happening, so this is the signal view, right? So in signal view, we'll see what is the signal that we are injecting. But if you want to use ramping modules for visualizing change in impedance, then we can actually go to the impedance view. Right now, we don't have any impedance characteristics. If I want to see the change in phasor, we can use the phasor view. So here we have the test has been completed and we have got the results of the last test. So what is the results that is being shown over here is the results of the last test. So to see the statistical values, let's just go to report view. So in report view, we'll be able to see the assessment statistics, right? So in assessment statistics, we can see what is the actual average value, the minimum value, the maximum value, and the standard deviation, calculation results, and calculation statistics as well. So this, if you want to run multiple repetitions of the same test in order to actually judge the performance of your protection relay, then repetitions and statistical analysis would play a major role in doing this. Now, one more point that I really wanted to show you here was the concept of IR plus and IY plus. So what is this plus? So plus essentially means that, so I'm going to start off with 1 over here and let's ramp up all the 3. So plus means how much you want to add to your original signal. So essentially it means that if you have IR as 1 and IR plus as 1, you'll be injecting 2 amps over here. So 1 plus 1. So if I want to start it off, so let's start off with 100 milliamps, because now let's do the same pickup value, right? So equal magnitudes and ramp number 1, ramp number 2 equal magnitudes from 100 to 200. So our pickup was somewhere around 0.14. So sorry, 1.14. So 1 to 1.14, that falls between somewhere between 100 to 200. And my DT is 100 millisecond, right? So 1 milliamps every 100 millisecond. Let's do the same thing over here. 0.2 to 0.1 minus 0.001, that is 1 milliamps, 100 millisecond. So now what we can see over here is, just press start, all the 3 phases. So it is just an addition, right? So how much on top of your original signal that we have actually performed. So here you can see that we have not changed the assessment. So 1 plus 1 plus 0.140, that is 1.140 would be your actual pickup value, right? So I can either assess it as a plus value or I can assess it as a individual signals directly itself. So it is up to me. So you can select your signals accordingly and you can specify the addition, that is the delta I plus del I, or you can specify the current directly itself. So this was a very simple example of how state sequencer or a sequence of events is possible in Omicron test universe, the ramping module as well as the statistical values we saw in this. And I don't want to save it. We are also looked at what is the state sequencer and how we can have multiple trip times, multiple time assessment, multiple states. Yeah. So coming up, we will be looking at the next week. We'll be looking at frequency protection. Now, this was a very important topic, and a lot of people has actually requested us about how to do this frequency protection, DF by DT. We will be looking at advanced ways of testing protection relays from the next week onwards. We'll be looking at under frequency, over frequency, but more importantly, we'll also be looking at the rate of change of frequency protection as per the standards. So there has been a lot of debate that has been going on about standards and which equipment could be used. So we'll see how that could be done as per the latest standards. And the week after that, that is on June the 27th, we'll be looking at voltage based protection. And thank you for joining me today. See you next time.